we're not all here. I guess this is everybody. I'm just glad we don't have an observer. We can just sort of relax now that we don't have an observer here. We can put our feet up and things. All right, Class 7. We have an exam a week from tonight. And I have prepared a little, it's not a sample exam so much as just a sample exam to give you an idea of like the form that the questions will take. So some of you have never had me in a class before and you don't know what my exams look like. This is what my exams look like. I've just given it to you. So part 1 are conceptual questions. And so on the conceptual part of the exam, you can't use your notes. There's no equation sheet, nothing, just the paper and your pencil and your brain. And so here's some typical questions I would maybe ask on a concept question. Briefly explain why seeding is sometimes required for bottle testing of BOD. Does anybody remember when we were talking about BOD bottle testing? So why would seeding be required? That wasn't the one that I had in mind. Let's see if the oxygen is already... Now that would be dilution. So, yeah, I'm talking about... Exactly. So, like just the classic example of if you put sugar in water and do a bottle test on just sugar water, there isn't going to be any decrease in the oxygen content because there's maybe no bacteria to use the substrate. So seeding is when you artificially add bacteria to the testing. So that's why sometimes you require seeding. So how long do you have to write? There's only going to be a little bit of space. For a conceptual question, I usually have 4 or 5 of those questions on one page. So you don't have a lot of room, and you should take that as an indicator of how much I expect you to write. Any one concept question, maybe you should think for 30 seconds and write for 2 minutes. It shouldn't be too long. 3 sentences, 4 sentences is plenty. So what is a combined sewer? For example, a response that I'd like to see for a combined sewer. A combined sewer carries both water and also wastewater. And the trouble with a combined sewer is that sometimes it will overflow during a wet weather event and it will discharge untreated wastewater to a stream. So that would be a full credit response to what is a combined sewer. Okay, now some of the questions are going to come from the vocabulary words that I gave you at the beginning of slides for each chapter. And infiltration is one of those commonly used terms in wastewater treatment that I think you should be familiar with. And infiltration is from broken pipes. That's when groundwater seeps into the collection network. And sometimes infiltration and inflow are measured together because it's hard to distinguish, when water's flowing through the sewer, it may be hard to know what was infiltration and what is inflow, but they do have specific definitions. And so if I ask you to define infiltration and you start talking about illegal connections from a roof drain, I'm going to take off points because that's inflow, that's not infiltration. Infiltration is groundwater seeping into the pipe. It may be during a wet weather event, but it is flow through the soil into a broken pipe. Okay, part D, what is the purpose of screening? So you just put in a short answer there about how you're trying to remove large particles that could either cause blockages in the pipe or could cause damage to pumps. And that's all you need to put. It can be a very short response and I'll see that you understand. So let me ask you I'll ask this one to you, part E. What's the purpose of recirculating sludge from the secondary clarifier into the aeration basin?
Once they're recycled and back into the aeration basin, they've been deprived of oxygen and they're hungry, so they're a lot more efficient at that stage than they were previously going through.
All right. That's definitely one of the important benefits of recirculating after it's coming from the bottom of the clarifier. The other thing you need to mention is that if we don't recirculate, then the biomass concentration in the aeration basin isn't high enough. So really, the purpose of recirculation is to get the biomass concentration higher, because just the natural biomass concentration is going to be very low, maybe what? Well, I don't want to speculate what it would be, but we need to get it up around 2,000 to 5,000 grams per cubic meter. So it's to increase the biomass concentration, and side note, recirculation also has the benefit of very hungry bacteria by the time they are recirculated. All right, so good. Any questions about what concept questions look like? About 35 to 40% of the exam grade will be based on concept questions. So that's talking about the points. And so maybe about 40% of your available time should be spent on the concept questions. Part 2 is problem solving. And in my experience, the engineers like problem-solving questions more than concept questions. It seems like my students don't like writing short answer and essays as much as they like putting numbers into calculators. So that's fine. I was the same way. You can use a one-page equation sheet for this part of the exam. And here are just a couple of sample questions. Some of these are derived from in-class exercises. B, that's a previous exam question I gave several years ago, and I didn't look at it. I think maybe the terminology for some of the variables may have changed in the newer edition of the book, but I've provided some answers there if you want to try and solve the problems just to see if you get what I got. So what should you take from this? It's just generally speaking, the level of difficulty you can see on the problems on the exam. They're going to be similar to the homework problems, similar to the in-class exercises, and so if you know how to solve the homework problems, not just did you solve it, but if you know how to solve it and if you understand the problem, then you'll be fine for the exam. But it's one thing to have the correct marks on the paper and turn it in and get full credit. That's not the same as understanding it. When I was a student, I turned in plenty of assignments where I had the right answer, but I didn't know why it was right or how I got the right answer. It's just I jumped through the hoops in the right order and ended up with the right number at the end. That's not enough on an exam. You have to understand it. So if there's still problems that you know that you did on the homework assignment but you still don't get it, look through the solutions that are posted or read through the book a little further or come see me for additional help if you need it. And I'll be happy to go over that with you. All right, so the exam next Wednesday. It'll be great. Also next Wednesday, we're going to have a brief presentation. We're going to have, I think he's the head of the Charleston section of the AWMA. It's just a professional association for air and waste management association. He's going to come and talk about some opportunities for student involvement in that professional organization. He'll only speak for maybe about 15 minutes, and then we'll get into the exam after he's done speaking. I don't know. I've got it in my email. I should have given you that. He's like the president of. Oh, I can look it up easy enough. Let me find it here. You'll probably know it. So. All right.
I get emails from about something that don't involve me.
Yeah. I have one other bit of exciting information. We're going to go tour the treatment plant. How many of you have never been to a wastewater treatment plant before? Have you been to a wastewater treatment plant? All of you? No? Okay. You've never been? Well, it's great. You can never be to too many wastewater treatment plants. It's worth it for the smell alone. But it's going to be the sights, the smell, the feel, the taste, all of it. We're going to enjoy so much. So you can either meet at the treatment plant at 5:30 or here at the engineering building. We'll leave at 5:10. It takes about 20 minutes to drive over there. And I'll give you the address and like a map next week. The 25th, that's the Wednesday after. So we're going to have the exam on the 11th. Then on the 18th, there's no class because of spring break. And then on the 25th, we're going to spend most of our class period over at the treatment plant. It gets dark about 6:45 or so. So I'm still debating whether we'll come back here for just a little bit more lecture or if we'll just do the treatment plant and that's it. I'm still thinking it over. Huh? We could do that comedy night? Yeah, when's the open mics at? Do you know? Okay, so let's see, tonight, not next week. So it wouldn't be on the 25th. 9? Okay, all right. So maybe it wouldn't work for the treatment plant, but that would be fun to do. Me too. So any questions about the announcements? All right.
Do we know anything about our second presentation?
Okay. So I got a question about the presentations, and somebody, I don't remember who, but they were wondering if the second presentation is related to your research paper, and it's not. The second presentation is going to be similar to the first ones where it was related to the book subject. Those second presentations will be on April 8th, so because we had to shift the schedule by a week due to the cancellation. On April 8th instead of on April 1st, and I'll give you those assignments next week so that you can start planning on that. Those are just going to be, it's going to be the similar thing where we slice up several of the subsections within Chapter 8 and assign each student to one of them. So I will give you that next week. Other questions? You know, time is really flying. This is class 7, but this is the 8th week of class since we missed one, and we only get to 15. So tonight is 8 out of 15. We're already past the halfway mark. So time's really moving along. So we've got a lot of ground to cover today, and we're going to start with a process that's called ANAMMOX. Are any of you here already familiar with ANAMMOX? It is really interesting. I wasn't familiar with ANAMMOX until just a few days ago. When I taught this course several years ago, I don't think it was in the book. It's actually a very new technology. It has some interesting history. You know, maybe 70 years ago, some scientists noticed that when they did a mass balance on carbon in a specific environment, I think it was in river sediments, they did a mass balance on carbon in some river sediments, and it just wasn't adding up. There was some of the ammonia that should have been there was missing, and they didn't know what it was, or maybe if the instrumentation was off, so they just sort of dropped it and didn't come back to it. Then in the 90s, they just in a wastewater treatment reactor were doing mass balances on ammonia and realized that it seemed like there were some constituents of wastewater that were breaking down ammonia without taking it to nitrate first. And so let's refer to the nitrogen cycle here. This is actually a really good diagram that summarizes what we talked about last week. Last week, you know, the big idea that we tackled was the nitrification, denitrification. And what nitrification, denitrification was is this nitrogen cycle is broken up into two different colors. Now this first part, N2 to NH4, humans do that. We're the ones responsible for taking nitrogen gas to NH4. And we do it by creating fertilizer and then applying the fertilizer to the land and eating the food that grows. And then, as they were saying in the video that we watched, you know, the majority of ammonia in wastewater, well, a lot of it anyway, is from human urine. So people are contributing the NH4. But then the rest of the process from NH4 to nitrite, nitrite to nitrate, and then nitrate to nitrogen, this was the wastewater reaction, where the nitrification process, there were some bugs in the aerobic reactor that was taking ammonia and taking it to nitrite, and then still aerating more, and it takes the nitrite to nitrate. And then it was in the anaerobic reactor that denitrification occurred, and during denitrification it was taking nitrate to nitrogen gas. And so this is just a really good summary of the nitrogen cycle that we were talking about last week. You notice that it's it's indicating that sometimes you have to add methanol as a carbon source during denitrification. So that's the traditional route. What the ANAMMOX process is they were able to commercialize this previous mystery. This previous mystery of, you know, where is the ammonia going to? This ANAMMOX process, it takes some of the ammonia is converted into nitrite, and once you have about 55% of the starting ammonia converted to nitrite, then there's these microorganisms that live on the inside of a little granule, and on the inside of this granule it's anaerobic conditions, and so the nitrite is passing through the membrane of this floating granule and into the anaerobic environment, and the microorganisms that are in there use ammonia and nitrite and convert it directly to nitrogen gas. And so that offers really a lot of big advantages over traditional nitrification, denitrification. If you look at this cycle, one of the big costs in wastewater treatment is aeration, because it's expensive to provide oxygen. You're having to use big electric fans to blow air into the water. And so you notice here is O2 and here is O2. And so traditionally, you're adding oxygen in two stages, the stage that gets you to nitrite and the stage that gets you to nitrate. In reality, these two reactions are happening in the same basin, but you require twice as much oxygen for traditional nitrification than you are for the ANAMMOX procedure. These ANAMMOX bacteria are using NO2 as the electron acceptor. And so the way to think about it is that these bugs represented in the diagram in red are eating ammonia and breathing nitrite. Instead of breathing oxygen, they're breathing nitrite. Now, they're not actually breathing it, but they're using it as the electron acceptor. And so the way that it works is that I actually have a video that shows the diagram of it. Before we watch that video, let's just step through what the benefits of this short circuiting are. The first is that there's a really high rate of nitrogen removal. It's very efficient and effective, and you can have a very pure effluent quality. You don't have to add methanol as a carbon source during denitrification, and you do have to do that oftentimes in traditional denitrification. Because you're aerating less, you save up to 60% of the energy that would ordinarily be required to remove nitrogen. This ANAMMOX has a really low yield, And remember, yield is a measure of, Y is a measure of the VSS that grows for some substrate consumed. And so it could be the COD that's consumed, or in our case, it's the VSS that grows for the NH4 plus that's consumed. And so a low yield is a good thing, because we want these microorganisms to eat a lot of food and not gain very much weight, because eventually we're going to have to dispose of the biomass. We're going to have to de-water it, and then we're going to have to landfill it somewhere or burn it. And, you know, whatever we have to do with it, it's expensive to get rid of. And so a reduced sludge production is really a nice benefit. And then the other amazing thing is that actually it generates less carbon dioxide. And so there are some greenhouse gas implications of some of the steps in wastewater treatment, and ANAMMOX has benefits of that. Now, it's not, unfortunately, it's not applicable to most wastewater treatment plants, not yet. You know, it's only been commercialized since around 2002, and there are only about 20 of these ANAMMOX reactors in the entire world. Most of them are for food waste, where there's a really high concentration of ammonium. The concentration of ammonium has to be above 100 grams per cubic meter, and that's very rarely going to be just a raw wastewater. You know, wastewater from a municipal source is almost never going to have ammonium concentrations that high, and so it's not really feasible to use it. The places that it's been used in the past has been a potato processing factory. There's a plant that makes yeast for baking. That's one of the places that this ANAMMOX has been implemented. The other issue is that the bacteria are thermophilic, which means they need temperatures in the range of 35 degrees Celsius, and so the water has to be pretty warm. And that's another reason why industrial wastewaters have been used in the past, is that industrial wastewater is usually warmer than municipal wastewater. You know, food coming out of water coming out of a food processing plant is usually pretty warm. So let's just take a look at this brief video that illustrates some additional facts about the ANAMMOX process. It sort of illustrates the little granules, and one of the amazing things, I think it's part of the patent that they have for the ANAMMOX process, is how they separate the solids and the liquids. So there's no sound on this, sadly. Usually we get really great music for our videos, but this one's silent. It's a Dutch company. And this process takes a while to get started, and so usually they'll seed the reactor with existing ANAMMOX bacteria flocks. So it's the granular biomass that allows it to have a two-step process in the same reactor. And these little red dots are illustrating the floating granules of bacteria. And you'd see the ammonia coming in at the bottom there. And they have to aerate it, so that's somewhat costly, but they're not having to aerate as much as they would during traditional nitrification. So there it is. On the outside are bacteria that are consuming the ammonia and turning it into nitrite. So there's the nitrite. The nitrite goes onto the interior of the granules, and those are the different bacteria that are consuming the nitrite and some ammonia and turning it into nitrogen gas. Now just on that equation it was showing, it looked like it was yielding a little bit of excess hydrogen ion. So I suppose it could be reducing the pH, although in the reading I was doing I didn't see anything where it was talking about it getting acidic over time. So that's how they separate the granules. There's an overflow at the top that basically just strains it. The effluent goes out the top, and over time you have to remove some of the granules because, you know, as low as the yield is, there still has to be some way to remove excess solids. If you didn't, the solids would accumulate in the reactor and it would fill up. So the same kinds of principles apply as in a traditional aerator clarifier, but it's kind of neat in this case that they don't need a whole separate clarifier. Because it's a granule, it's really easy to settle and strain, and so they don't have to have a clarifier downstream. And they also don't need to like oxygen starve the bacteria because it's happening in a steady state kind of a thing. It's not like in a clarifier, at the bottom of the clarifier the bacteria are being stressed. You know, they don't have enough oxygen, they don't have enough substrate, so when you recirculate them they're hungry and ready to eat again. That's not happening in this case. It's like on a continuous loop. So it's really an interesting application, and So I suppose we'll probably see a lot more of these. I don't think there is an ANAMMOX in the United States yet. I think that the applications are exclusively in Europe, and there might be a couple in Asia as well, but as far as I'm aware, not one in the United States quite yet. Some of the operational issues that come into play when you're utilizing this technology is that if there's too much nitrite, then it can inhibit growth. And that's a little bit counterintuitive because remember, it's nitrite that it's using as food. So let's go and take a look at this. So in the first stage, you're converting some ammonium to nitrite. But if too much of it builds up in solution, like in the aeration tank, if there's too much nitrite, then it can inhibit the reaction. So, you know, the concentration shouldn't go above 60 grams per cubic meter. And then the other thing is that on the inside of those bacterial flocks, those are strict anaerobes. And so the oxygen concentration that should be inside of the reactor, they sometimes have to fine-tune that oxygen concentration depending on the thickness of the granules. So like in the startup phase before you really reach steady state in the reactor, the granules may be relatively small so that the thickness of the anaerobic layer isn't very big yet. And if there's too much oxygen in the reactor when you're starting up, then that can inhibit it from growing. And so they may be a little bit stingy on providing dissolved oxygen at the beginning just to make sure that the strict anaerobes on the center of the granules don't get exposed to too much oxygen. As I already mentioned, that this is not a quick process to kickstart, and so they've seen that really you don't see removal of ammonia until about 10 to the 10th cells per milliliter are present in the reactor. So the concentrations that are required are quite high, and so they'll seed the process to begin with just to prevent a startup of several weeks. And then the other thing is that this has some potential to be used in other things besides wastewater treatment, other industrial applications, although we are interested in using it for the reduction of nitrate after the ammonia is turned into nitrate. The bacteria themselves can also use formate, acetate, propionate. There are other substrates that it could use, and so it may be that this becomes kind of an application that's used in other areas of chemical engineering. All right. In Chapter 7, Section 12, it's talking about some of the atmospheric pollutants that can come out of wastewater treatment. And this is a new section of the book that's just been added since the last edition, where they're trying to focus more on energy reuse and reclaiming nutrients out of wastewater and some of the big picture environmental issues. And the point that's made in this section of the text is that actually when you convert nitrogen into nitrogen gas, sometimes a fraction of that will turn into nitrous oxide. And nitrous oxide, did anybody here see the Fast and the Furious? I won't ask you to raise your hand because we'd all be embarrassed that we've probably seen one of those movies. They're so dumb. But NOS, you remember like that, they turn it on, all of a sudden their car is going really fast, NOS. You got to push the NOS button and then you start going fast. Well, that's nitrous oxide. They add a little bit of sulfur into the gas that they sell for automotive use just so that people don't breathe it and get high. Now, they try and make it objectionable because also nitrous oxide, the other application is like when you go to the dentist, that's the laughing gas that they'll give you for pain relief and kind of knock you out a little bit while they yank out your wisdom teeth. So, okay, wastewater treatment generates nitrous oxide, and as you can see from the diagram here, nitrous oxide is a greenhouse gas. And so here's just a diagram showing that of the constituents that are in the atmosphere right now, we usually talk about CO2 as the biggest greenhouse gas. And on a mass basis, there's more CO2 accumulating in the atmosphere than anything else. But it turns out that methane is even more effective at insulating outgoing radiation than carbon dioxide is. But nitrous oxide is 300 times more efficient at reflecting outgoing solar radiation back towards the Earth again. That's just, I think, a function of the ability of different chemicals to act as reflectors. You know, they have different shapes and the wavelength of the radiation that's emitted. And so nitrous oxide, when it accumulates in the upper atmosphere, can be very damaging. And then the other thing about it, besides being a reflector for outgoing solar radiation, which makes it a greenhouse gas, it also depletes ozone. So it's sort of like a double whammy. It causes lots of problems. There's another gas that's sometimes emitted during nitrogen removal and wastewater treatment, and that's nitric oxide, NO. Now, nitric oxide isn't a greenhouse gas, and it's not going to deplete the ozone layer, but what it does do is it can turn into nitrogen dioxide, NO2, which when that gets into the atmosphere forms nitric acid. So it's a contributor to acid rain, and also will cause smog at ground level. So like if you've ever been to Los Angeles before, you've seen the terrible smog that they have in Southern California, and there are other places too. But a lot of that is due to nitrogen emissions from cars. Some of it's due to nitrogen emissions from fertilizers and also wastewater treatment. So this is just illustrating the importance of the ozone layer as it filters out UVB rays. And when you have a chemical like nitrous oxide that's depleting the ozone layer, then that can cause problems to vegetation, and humans can get higher rates of skin cancer, especially at the polar regions. So how does that happen? Well, it's during the denitrification process that a small fraction of the nitrogen goes into the gaseous phase. This is the pathway that we illustrated last week. The pathway of nitrate going to nitrite, and then nitrite eventually ending up as nitrogen gas. There's a couple of intermediate reactions along the way. It's these intermediate reactions where these are soluble in water, but a fraction of it is going to volatilize and get into the atmosphere. So during these intermediate reactions, if they're slow and there's an accumulation of NO and N2O, then it can turn into greenhouse gas and acid rain and promote smog. Unfortunately, it can also happen during ANAMMOX. You know, the great latest, you know, that wonderful process that uses less oxygen and is faster and more efficient, less sludge. Well, there's also the possibility that we'll have the formation of those gases even during ammonia oxidation. So we can have our wastewater treatment contributing to air pollution. But there is a way to limit that and control it. We don't have a lot of options, but what they have found is that sometimes the speed at which the nitrite goes to nitrogen gas is partly governed by consistent dissolved oxygen concentrations. It's when the dissolved oxygen concentrations fluctuate a lot that it seems that there's the most emission of air pollutants. And so a reactor that is not in steady state is going to emit more air pollutants than a reactor that they can keep it steady and the bacteria aren't stressed and there isn't an accumulation of any one of the chemical constituents along the way. So any questions about air pollution and wastewater? Okay. So nitrogen is just one of the nutrients that we need to try and limit when we discharge wastewater to a receiving body. The other big one is phosphorus. Phosphorus can promote eutrophic conditions. And so here's a picture of algae, and I think that this picture was taken in Tennessee. It looks like they've really bumped up the saturation. I think they photoshopped that to make the algae look especially bright. I've never seen algae that bright, but still it makes the point that an algae-filled stream, it's not as attractive as a nice clear stream or blue water. green water somehow just seems wrong. Now, phosphorus is in water as orthophosphate. That's the soluble form of phosphorus. And you know, one of the main sources of phosphate getting into receiving bodies is fertilizers. And so when you add fertilizer to the lawn to make it green and grow well, that contributes to phosphorus ultimately getting into the Gulf of Mexico and causing red tide and algae blooms. Until maybe 5 years ago or 10 years ago, it was pretty common to load dishwasher detergent with phosphorus. Does anybody know why they would put phosphorus in detergents? It helps. It helps the surfactants. It doesn't cause the bubbles, but what it does is phosphorus ties up calcium, iron, manganese. Phosphorus temporarily will bind to hard water, polyvalent cations, the things that cause hardness in water. The phosphorus can temporarily keep it busy so that the detergent is able to foam and be more effective. And so it's a water softening agent, phosphorus is. And so that's kind of why dishwasher soap doesn't work as well as it used to. Around here we have hard water. You can have your own water softener in your house, with rock salt where it does ion exchange. I don't have an ion exchange water softener at my house. If I did, my clothes would be softer and my dishes would get cleaner, but I don't. So Cascade and the really nice soaps, until recently, they'd put in a dose of phosphorus to try and keep the water hardness a little bit lower. But they don't do that anymore because there are stricter water quality regulations. They're trying to limit how much phosphorus gets into the water. So what I want you to understand is the difference between orthophosphate and polyphosphate. Orthophosphate is the soluble version of phosphate. It's just when phosphate isn't connected or bonded with anything else. And what you can see is that phosphorus is connected to 4 oxygens here. It's PO4 3-. And so there's 1, 2, 3 oxygens that have just a single bond with the phosphorus, and then one of the oxygens has a double bond with the phosphorus. So what's the charge of phosphorus in this chemical? No, the phosphorus itself. Yeah, the complex has a -3, but what is the charge of the phosphorus? It's getting, what is it? 5. Right. So it's getting 2 there. It's tying up 1, 2, 3, 4, 5. So it's +5. The phosphorus itself is +5, but the complex is a -3. Polyphosphate is when groups of the phosphate ion are bound together, and it's insoluble, meaning it precipitates. In drinking water treatment, they'll commonly add a mix of ortho and polyphosphate, especially when it's groundwater, that they're pumping groundwater and sending that into a distribution network. When I was in graduate school, I was living in Indiana, and all of the water treatment plants that I went to, which was mostly groundwater, they would mix up their own blend of ortho and polyphosphate. And the reason why they did that was that the orthophosphate prevented the hardness. There was a lot of iron and manganese in the water in Indiana because it was groundwater, and so they'd add a little bit of orthophosphate, because if they didn't, then the iron would start to oxidize, and someone would fill up the tub with water, and the water would look orange or black to them, and people think, oh, the water shouldn't be orange. The water's not supposed to be black. And they'd think it's polluted water, but really all it was just iron or manganese. And so the orthophosphate, the objective of adding a little bit of orthophosphate was to keep the water softened and just to tie up the minerals. And then they added also a little bit of polyphosphate because they knew that that was going to help precipitate calcium onto the pipes. And so it helped prevent corrosion. This is a corrosion control chemical, because if you just put distilled water through a steel pipe, the distilled water will actually dissolve the steel pipe over time. It will cause corrosion and rusting. And you don't want to have rusting of the pipe, and so having it so that your pipe is just precipitating a very, rather the water is precipitating a very thin layer of calcium phosphate onto the pipe. You know, over the long term, over 30, 40 years, the pipe will get covered with scale, but that's better than having the pipe corrode and rust through. That's a little bit more information than maybe you need about ortho and polyphosphate, but it's actually going to come in important because the bacteria that can remove phosphate from water, they are cycling between orthophosphate and polyphosphate. And so what you need to remember is which one is the one that's soluble in water and which one precipitates. Orthophosphate is the one that gets into the water and dissolves. Polyphosphate either has to be precipitating, which means it's going to form a salt that settles out of solution, or polyphosphate can be inside of cells. So a microorganism that incorporates phosphorus into its cell mass, it's doing that in the form of polyphosphate. So why do we want to remove phosphorus? What's so bad about phosphorus? Well, if there's too much of it, it stimulates growth. It can stimulate algae growth. It can stimulate the growth of cattails and aquatic weeds, just things that we don't want happening. And so the typical treatment plant permit would maybe be in the range of, they have a permit to discharge between 0.05 and 1 milligram per liter of phosphorus. That's sort of the typical range of what the effluent concentration is allowed to be. One of the ways to get rid of phosphorus is just precipitate it out. We don't have to use biological treatment. If you want to use chemical treatment, phosphorus will precipitate readily, but the disadvantage with that is that you have to constantly buy the chemicals, and so that can be more expensive than biological removal. And so that's why, oh, and then you have to dispose of the precipitate somehow. You're still going to have like a sludge that needs to be dewatered and disposed of. And so it doesn't really solve all your problems. Biological removal, here's an acronym for you, EBPR. The book is talking about enhanced biological phosphorus removal, and it's generally taken to be less costly than chemical precipitation. Do you have a question I can answer? No? Okay. It generates less sludge volume because some of the, well, it's generating less sludge volume because you're not adding another chemical to get rid of the phosphorus. You know, if you think about when you add alum or ferric chloride, the salt that forms is including the phosphorus, but also all the chemical that you poured in. Whereas in the case of a biological removal, your yield may be, well, it will be less than 1, and so there's that, and then you also didn't add another constituent. So that's why there would be less sludge volume. And there's maybe some possibility of recovering the phosphorus and reusing it as a fertilizer. The sludge that comes out of enhanced biological removal, it can be worked into fertilizer or mulch sometimes. So here's the strategy, and this is the sort of thing I'd like you to be able to explain on the exam. You know, on these conceptual questions that I ask, this is a good example of a conceptual question concept that you can expect to see on the exam. What we want to do is the types of bugs that can use up phosphorus, they're very weak and they're slow. The other microorganisms can always outcompete these PAOs, the phosphorus accumulating organisms, unless we create a special environment where they have an advantage. It's like we want to create a certain spot where the PAOs can grow, better than the other microorganisms can grow. And so what can we do to give them a competitive advantage? This is a diagram that illustrates an environment where microorganisms that accumulate phosphorus have a competitive advantage. If you take the sludge from the clarifier, normally what we do is we would put the sludge into the aeration basin. But in this case, what you can see is that we're going to take it just to a small anoxic basin. Anoxic means that there's no aeration in this small anoxic basin. The residence time in this anoxic basin may be only 30 minutes or so. It's a relatively small basin. But by returning the sludge there, the microorganisms that accumulate phosphorus in the anoxic basin, they'll eat the substrate, but the normal aerobic bacteria, they require oxygen, and so they can't eat the substrate in this anoxic basin. And so that's our selector, as it's called. A selector means an environment that favors one species over another. And so the anoxic environment favors the PAOs, and when they're in the anoxic reactor, what they're doing is they are using their body mass to release phosphorus. And that's actually counterintuitive, because remember, the whole purpose of this process is to get them to absorb phosphorus, not to release it. So in the anoxic zone, it's like they're sweating phosphorus, and that seems bad, but after they lose the phosphorus in the anoxic basin, when they get into the aerobic basin, they realize that they've lost a lot of phosphorus, and so they start taking it up very, very quickly. And so, in a way, we're tricking the bacteria. In this anaerobic basin, they're the only ones that can eat in the anaerobic basin, but while they're eating in there, they're using up their stored phosphorus. And so then they get into the aerobic basin and they realize that they're out of balance. They've eaten a lot, but they don't have enough phosphorus. So then in the aerobic basin, they don't have good access to the food, because the other microorganisms, the aerobic microorganisms, are out-competing them for the substrate, but what there's plenty of, nobody else wants the phosphorus, and so these PAOs are trying to get back into balance again, and so they take up an excess amount of phosphorus. And so then the cycle continues. Some of them are returned, and some of them are wasted. So that's the trick, is by starving them of oxygen, we get them to panic, and then when they come back into the aerobic basin, they take up more phosphorus than normally they would. Like if we just had them in aerobic basin, it would never work. It would never work, because remember, there's two reasons why it wouldn't work. Number one, it wouldn't work because normal bacteria would eat all the food before the PAOs had a chance. But then the other reason why it wouldn't work is that they would only take up a little bit of phosphorus. Even if they could eat, they'd only take up a little bit of phosphorus instead of a lot. You know, we're sort of, this is biological engineering at the finest, finding some way to trick the bacteria to do the work that we want them to do. So any question about that cycle?
So is that common in most treatment plants, or is that special?
No, it's called tertiary treatment. You know, like I don't know what we'll see at the Huntington plant, but I don't remember ever seeing phosphorus removal at any of the plants that I've been to.
How do they handle it at those plants, or is it just not needed?
It's usually just that the phosphorus concentration is already low enough that they're going to be able to hit their limit, or that there's a minor amount of phosphorus removal in just a normal aerobic basin. Are you saying you've never seen it either? Phosphorus removal?
No, it's kind of like you asked, the main reason it's not is maybe it's fertilizer and stuff, so it's most of it's
running off.
In rural areas, and you know, in cities don't have the fertilizer and the things that would be contributing to that.
Yeah.
So it's kind of
Good point.
phosphorus is where the wastewater treatment plants aren't. I've seen some increased stuff with some little package plants put up in the
Mm-hmm.
put a
So like a feedlot or something?
Yeah, we had a school that was in a valley with farms all around it, and they wanted to treat this little farm. So that
Yeah. Yeah, so I guess most of the phosphorus is non-point pollution, meaning it's going to be surface runoff off the land into the river. But there are some cases like industrial wastes, or the point that he made about when you have an accumulation of runoff in one spot. So it's tertiary treatment, not super common, but still interesting, even if we don't see it very often. I think it's really interesting that we can create this selector that favors one group over another. Seems like discrimination, right? But it's in a good way. It's good discrimination because in the anoxic basin, these organisms can really do something special.
There's only that we would actually put phosphorus on things like laundry detergent and stuff, right?
You mean, how would it be getting into
Like our wastewater.
into municipal?
Yes.
Yeah, so it would be detergents, or there's some cleaners like, what is it called, CLR, calcium lime rust. You'd use it maybe for cleaning off bathroom tiles. It's phosphoric acid.
We just put out very minimal amount.
Right, you don't use a lot of it. And like I was talking, they sometimes put it in drinking water, but it's usually at pretty low concentrations in the drinking water. All right. So a little bit more detail. We went into the basics of what's happening in this diagram. So here's more detail. BSCOD, that means biologically soluble carbonaceous oxygen demand. That's fermented to acetate, and the PAOs are actually consuming acetate inside of the anaerobic zone, and then they're also using up their stored polyphosphate. And so remember, which one is polyphosphate? Is that the one that is soluble or insoluble? Insoluble, right. So in the anaerobic zone, they're turning the polyphosphate, which we can settle. That's good. We want to settle out the phosphate. We don't want it dissolved. So they're doing this sort of dangerous, bad thing. They're converting it to orthophosphate, which means that actually inside the anaerobic zone, temporarily the phosphorus concentrations are increasing because they're shedding phosphorus. And in the process, they are producing these storage products. They have some energy that they're storing. And then in the aerobic zone, they're using their stored energy, because remember, they can't just use the normal COD in the aeration basin. In the aeration basin, they're being outcompeted, and so they have to use their stored energy, and then they are taking up orthophosphate to form insoluble phosphorus in their cell components. So new cells are formed, and there's a lot of phosphorus in those new cells. Here's a diagram that's found in the book, and I think this is a very important diagram. This is a good short answer diagram. I could just show you a picture like this, and I'd say, explain this picture. And so what I would want you to explain is, why does the phosphorus concentration go up in the anaerobic zone? Because that's what it's saying, is that at the beginning of the anaerobic zone, the concentration of phosphorus is going up, and before it starts going down again in the aeration basin. So how come? Does anybody remember, why does the phosphorus concentration temporarily increase?
Because when they get the anaerobic tank, they're releasing the phosphorus.
Right.
And then
They're releasing the poly into ortho. So, and ortho is soluble. And then here in the aeration basin, you can see that they're using up the ortho out of the water, turning it into polyphosphorus. And so, like, mass cannot be created or destroyed. So the same mass of phosphorus is inside the aeration basin at all times. There's the same overall mass. It's just it's converting it from one form to another. It's converting it from ortho to poly. And so you can see this line here says ortho, and the ortho is going down. That's good, because it's the ortho that we could never settle out otherwise. But once it's incorporated into the cells, later on in a clarifier, we can settle those cells, and then we can dewater the sludge, dry it out, recover the phosphorus. All right. In the end, these organisms, the PAO, they'll have between 20 to 30% of their dry weight will be phosphorus. And that's incredible that they can accumulate that much. A normal bacterial cell would normally have less than 1% of its dry mass be phosphorus. And so this is a special microorganism, and it's even more special because we tricked it to take up more phosphorus than it normally does. If we didn't go through this cycle of starving it temporarily, it would maybe only accumulate maybe 10% of its dry mass as phosphorus. But it takes up 3 times as much because of the temporary anaerobic zone. One of the nice things about phosphorus removal, here's a scanning electron microscope, and you can see that the sludge is very dense, which means that it settles nicely. Sometimes the sludge particles are very small, the flock isn't very big, and you'll remember when we were doing settling velocities that the bigger the diameter of the particle, the faster it falls through the liquid. So big particles settle quickly, small particles settle slowly. And so one of the advantages of removing phosphorus is that the sludge that forms has a big diameter, which means it settles very easily. So it doesn't have to be in the clarifier for very long. And that's fortunate, because if it was in the clarifier for very long, we'd be in trouble. Because remember, it'll start to go from polyphosphorus to orthophosphorus if it's not getting oxygen. So let's go back to this previous diagram. What happens in anaerobic conditions? In anaerobic conditions, it starts shedding its stored insoluble phosphorus into a soluble phosphorus. And so look at, here's some nice bubbling sludge. Doesn't that look like the sludge is, like, they've got these aerators in here. You really have to aerate phosphorus-containing sludge a lot, because if you don't, then all that work you went through of concentrating the phosphorus will backfire, and it's just going to release all of that stored phosphorus into ortho. And so that's just one of the operational concerns, is that when you accumulate the sludge, you're going to be taking it off the bottom of the clarifier. When they temporarily store the sludge before dewatering it and drying it, they really have to aerate it. Otherwise, you've just got a water pollution problem again. You've got a higher concentration of dissolved phosphorus than you had before. So you don't want it to go back into solution. As far as the growth kinetics goes, it has sort of typical growth comparable to other bacteria. Usually the mean cell residence time, SRT, is greater than 2.5 days. That's a function of what fraction of the sludge is recirculated versus wasted. And it can grow relatively quickly, like you'll notice from the maximum specific growth rate that you can have up to 0.95 grams of cell mass per gram, increase in cell mass per gram of original cell. So these cells are dividing quickly. You can double the mass of cells that you've got on a daily basis. To prevent the ortho forming, the dissolved oxygen concentration should be above 1 milligram per liter. There's also some concerns with the pH going too low, or if you don't have enough of these other trace nutrients, then the phosphorus accumulating organisms can't grow and thrive unless you've got also some magnesium and potassium and calcium and so on. Okay. In section 14, it's talking about anaerobic treatment. So the benefit of anaerobic treatment is that it may be slow, but it's very, very complete. It's a way of breaking down the waste in the absence of oxygen. And so having anaerobic treatment of wastewater has a really low yield, which means you're not generating too much sludge based on how much substrate it's removing. It also has the ability to generate methane, which can be used to heat up the water that's in anaerobic treatment and make it go faster than it would if it wasn't being heated. Usually it would be very uncommon to generate so much methane from anaerobic treatment that you can actually do a lot with it. I think there was some recent announcement like Bill Gates was drinking wastewater. Do you remember hearing about that? So I think that some of that process was powered by anaerobic treatment of the waste. They were breaking down the waste anaerobically and using the methane to treat some of the water. But usually you can only just get enough methane gas off of anaerobic treatment. They'll usually just burn it to heat up the waste that's being treated, and that's it. But it's slow, which is why you have to have a really large reactor. They call it an egg-shaped reactor, and anaerobic reactors are shaped in an uncommon egg-shaped way because it helps with mixing. It was found in Germany a long time ago. They found that it was just more efficient to have mechanical mixing if it was egg-shaped, and so it just helps to make sure that there's not too much stratification inside of the reactor. So I've got a video to show you here. This was actually, I think it's someone's class project, some students, but there's some good stuff on here anyways. Let me turn off this.
They produce organic acids out of the sludge carbohydrate. Another group is the methanogen. They are archaea that produce biogas from the organic acids. The anaerobe can perform sludge digestion at biophilic or thermophilic range. However, the mesophilic range is conventional for an acceptable digestion rate and energy input. For anaerobic sludge digestion to happen, a minimal COD concentration of 1,500 grams per cubic meter is required. Ammoniacal nitrogen concentration should be above 50 grams per cubic meter, but below 1,500 grams per cubic meter to avoid inhibition of the methanogenesis. Phosphorus content should be higher than 10 grams per cubic meter. Sulfur should be kept at a range between 35 to 50 grams per cubic meter to maintain bacterial growth and methanogenesis. Some heavy metals should be kept below a limit as shown below. The pH should be kept as neutral as possible. Once all conditions are met, the sludge will be firstly hydrolyzed by the exo enzymes secreted by the bacteria into simple sugars, amino acids, and long-chain fatty acids. Then, these intermediate products are further transformed into alcohols, volatile fatty acids, ammonium acetate with inorganic hydrogen gas, carbon dioxide, and hydrogen sulfide by acetogenesis. The acetogens then convert alcohol and volatile fatty acids into acetic acids while producing more hydrogen gas and carbon dioxide. Finally, the methanogens uses acetic acid, hydrogen gas, and carbon dioxide to generate biogas. The digester can be designed as a shallow cylindrical tank, a tall cylindrical tank, or an egg-shaped tank. In general, cylindrical design has less efficient mixing and promotes scum and foam accumulation. In contrast, egg-shaped reactor is cleaner of scum and foam, more efficient in mixing, but may require additional biogas storage tanks and sophisticated construction. A suspended growth single-stage digester is the conventional technology applied for anaerobic sludge digestion. The sludge is fed into the digester and get completely mixed. The lighter gas will be collected on the reactor's top, whereas the sludge is reduced by 40 to 50% of its total solid after 30 minutes to 24 hours.
All right. So he jumped through the chemical reactions kind of quickly there, and we'll take a second look at that. But there were some nice pictures there to give you an idea of the variety of reactor configurations that are used. So hydrolysis is where the three primary energy sources are broken up into simpler components. Typically in wastewater, there is going to be some fraction of it that exists as carbohydrates, some proteins and lipids, and actually all three of those constituents can be eventually turned into methane. The carbon in all three is going to be transformed through, first, hydrolysis just means the wetting or the breaking it apart. Fermentation or acidogenesis is where monosaccharides, amino acids are forming. Acetogenesis, and finally methanogenesis. And so in hydrolysis, it's actually not bacteria that are doing it, that are breaking it down, but it's the enzymes that are emitted by the bacteria. And so the bacteria are sort of excreting a chemical that breaks down the particulates and lipids. And the similar thing happens in the human mouth, actually. You may have heard that you actually start digesting your food before you even swallow it. But there are enzymes in your mouth that when you're chewing food, the enzymes in your mouth get into the food and start breaking it down through a chemical reaction. And so that's similar to what's happening in this anaerobic reactor through hydrolysis. It's an initial breakdown due to the enzymes. Fermentation is volatile fatty acids, VCA. Volatile means that it would evaporate. It has a high partial pressure in liquid. And the bacteria are doing that through direct action. And they're already generating acetate, propionate, butyrate. These are high energy chemicals through acetogenesis. It converts it further, and it's the methane that ultimately we want it to generate so that we can burn that. The methane is the usable energy supply, and it does that through methanogenesis. The problem with this process is that sometimes during anaerobic breakdown of any kind of a substrate, if there's sulfur present, then it can form hydrogen sulfide. And this hydrogen sulfide is a gas that you probably would recognize it if you smelled it. Sometimes we have hydrogen sulfide smell here in this building. Like when you walk in the doors, you can sometimes have a smell. You maybe think it's natural gas, but what they've tested several times and found out is that there's drains in the engineering building that there's stagnant water, and underneath that it's whatever scum is in that drain is being broken down. Sometimes they'll see hydrogen sulfide accumulation in sewers that have really low flow rates and the wastewater isn't mixed. The problem with hydrogen sulfide is that it's toxic to humans and it actually can corrode pipes. But also in the context of wastewater treatment, the problem with hydrogen sulfide is that it's toxic to the methanogenic bacteria, and so it slows down the generation of methane, which is the whole point. And so it's important to control for sulfur and make sure that there's not too much sulfur previous to the generation of methane. So we're about halfway through the class. Let's take a 5-minute break, and when we get back together, we're going to do in-class exercise number 7. And we will come back to it if we have time. Okay. So we were talking about turning biomass and COD into methane. A few of the other little smaller subjects that get addressed by the remaining sections of Chapter 7 are how to remove toxic and recalcitrant organic compounds. And it introduces some new vocabulary in this chapter. It talks about xenobiotic compounds. And a xenobiotic compound is something that's just unfamiliar to natural living tissue. It means that it's synthetic. So it wouldn't exist in nature except for humans made it. It may be chlorinated compounds like dry cleaning fluid, just any kind of non-naturally occurring chemical. And it says that some of those compounds are refractory. This term refractory means that it's difficult to break down using conventional treatment. If you put any of these compounds through a normal wastewater treatment plant, the wastewater treatment plant would either be damaged by these, or it would just pass through without anything happening. Some of them are actually antagonistic to the bacteria that live in a treatment plant, and some of them, the bacteria just don't know what to do with it, and they pass on through. So you can see the list includes petroleum products, halogenated solvents. This term halogenated, the most common halogen that we see in chemicals is chlorine. And chlorinated solvents are frequently used as degreasing agents. You've probably heard of dry cleaning. You know, expensive clothes sometimes aren't supposed to be washed in water. They're supposed to be washed in, they say, dry clean only on it. And it's not that they're cleaned in a dry way. It's that they're cleaned with non-polar solvents, like chlorinated solvents, that are actually really bad and toxic if they get into the environment. And there's just a few of the bacteria that can break down chlorinated solvents. So you see there's a list of these types of organic compounds that we're not usually very good at removing in wastewater treatment plant. The good news is that most of these shouldn't be present in our wastewater. If you think about it, you shouldn't be flushing gasoline down your toilet, and you're not supposed to dispose of chlorinated solvents into a combined sewer. So usually the concentrations are relatively low. We know the most about the removal of these types of chemicals just from specialized instances of the wastewater being broken down in industrial situations. Here's a picture of a pulp mill in Sweden. One of Sweden's big exports is lumber and paper, and the Swedish are very good at making sure that their industrial activities don't contaminate and pollute their water supplies. And there's a lot of really nice rivers and lakes in Sweden, and this is a really effective treatment plant. But one of the ways they've learned about how to remove solvents like chlorinated solvents from wastewater is that one of the things you have to do in paper is bleach the pulp. You know, paper isn't white naturally. If you think about the color of wood versus the color of paper, the way they make paper white is by bleaching it. And so that bleach has to be treated and removed from the water before it's discharged into the stream. And so we know a lot about how to remove these chemical constituents from water based on industrial applications. Here's another instance where sometimes PCBs or dioxins can be in wastewater, and one thing that the General Electric Corporation has had to do is spend literally billions of dollars dredging the Hudson River in upstate New York, because back in the 50s and the 60s they were discharging PCBs directly into the river. They just dumped this highly carcinogenic chemical into the river, and it causes a lot of problem with the fish that are there. You can't eat the fish that are in the Hudson River in the vicinity of this area. And so for the last 5 or so years, they've been dredging it, and the first phase of that project, I think, is nearing completion. We actually won't watch the video, though. Don't have time for that. It's just shows the scooper. It's removing river sediments and how they eventually have to landfill that to treat it. In order to treat some of these trace organics, it's specialized bacteria that can break them down. They're kind of rare, exotic species, and so if you do have a treatment plant that is going to be receiving an industrial wastewater that has one of these trace organics, usually to get good removal, you have to sort of colonate and populate an aeration basin with the species that are required. And so again, we're talking about seeding, because the initial thing that we need isn't there. And so even when you do seed, it still may take several hours up to several weeks before the bacteria are healthy and hardy enough to come into contact with the wastewater and start breaking down the constituent that you're trying to remove. The text makes the point that sometimes these trace organics only occasionally are coming to the treatment plant. Maybe you'd only sometimes have insecticides. If you think about the way that farming works, is that they'll spray the fields, or they'll spray the crops maybe 2 or 3 times through the summer, and so then there's a runoff of the pollutant, and it may get into the wastewater treatment plant. And so if you had biological treatment of something that's only coming occasionally, then in between the application of the pesticide, whatever microorganisms break it down are going to starve. And so it's not good to have the periodic surge of the pollutant coming through, because in between instances of that flow, then the degradation stops and the microbes themselves may be eliminated. The way that the biodegradation can occur, it may be that there are microorganisms that just use these organic materials as a substrate. It might be that they're food, and usually that excludes chlorinated compounds. There are only a few microorganisms that can actually consume and eat the chlorinated compounds. Another possibility is that instead of a substrate, they're using whatever the bad compound is as an electron acceptor in place of oxygen. So instead of breathing air, they maybe would be breathing or using as an electron acceptor some of these other chemicals, like explosives may be a good example of something that they could use as an electron acceptor. But the most common biodegradation pathway is what's called co-metabolic degradation. Co-metabolic means that it just sort of incidentally takes it up into its body mass without really intending to. It's just sort of coincidental that it does. The abiotic losses means the non-biological removal of the constituents, and the removal of these bad chemicals may just happen because it is attracted to the organic material in the biomass. And one thing to remember about that is that organic chemicals are attracted to other organic materials. And so who here has ever drank water from a Brita filter? Have you ever seen the little filters? You put it in your refrigerator as a small cartridge, and you take it out of the fridge, pour water, and then you fill it up again. It's just a cylinder. And does anybody know what's inside those little cylinders that you put into a Brita filter? It's carbon. Yeah, exactly. Activated carbon. So all that really is it's coal. I mean, it's coal that's been purified and crushed. And so why do they put coal, essentially, as a water filter? What's the purpose of that? How does it work? Do you know? Okay, it does have a high surface area, so that's part of it, and that's an important part of it. The other way it works is that the chemicals you're trying to remove are attracted to those little granules of carbon. Carbon is attracted to other carbon. And so the liquid chemical, like the spill that they had in Charleston last winter, I felt very comfortable because I have a carbon filter on my drinking water at home. It's a block of porous carbon, and so I didn't feel so worried about drinking the water, although they said it never got bad where I live, because I don't live in Charleston. But so here, in a wastewater treatment plant, the biomass, the mixed liquor volatile suspended solids, MLVSS, that can act as a surface that some of these organic compounds just naturally sorb onto. And so what this rate here is showing the rate of absorption. It's the chemical not being eaten by the bacteria, but it's the rate of the chemical just sort of absorbing onto the surface of the biomass. Another place that the chemicals can go is just volatilizing. That volatilization, it means it's evaporating out of the solution. And it's a very simple thing to estimate the rate of volatilization through a surface area aerator. If you're using diffused aeration, meaning that at the bottom of the tank we have the air bubbles coming up, then estimating the rate of evaporation is a little bit more complicated, and it depends on obviously the rate that oxygen is being added to the system, the depth of the reactor, the volume of the reactor, and so on. Finally, the last thing that the text talks about is, I think this is the last section, 716, trace organics. Oh, metals, right, heavy metals. Who could forget heavy metals? All right. All right. Trace organic compounds is kind of a hot new topic because they're finding that there's these very small concentrations of pollutants in wastewater, and one of the things they're worried about is not that it's toxic in the same way that gasoline or explosives or fertilizers are toxic, but these chemicals can mimic human hormones. And so here I've got a picture of antibacterial soap that has a chemical that's called triclosan. It's the active ingredient in antibacterial soap. And they're starting to find that triclosan mimics estrogen. And so estrogen is a hormone that is found in women, and so it's mimicking the action of estrogen. Trace organics may be pharmaceuticals that get flushed down the toilet or naturally excreted by humans after they're consumed. It can also be things like toothpaste or fragrances. All of these things have been found to mimic hormones that are supposed to be limiting growth and only present in living tissue at a certain concentration. So even though the concentrations of the wastewater treatment plant are very low, in the range of nanograms to micrograms, that those concentrations are enough to affect the organisms that are living in the discharge stream. And so here's an example of frog that has multiple legs. They found frogs that are male frogs that develop female reproductive parts because of exposure to estrogens that mimic naturally occurring hormones. And so even though the concentrations are low, there's a lot of attention that's given to what are sometimes called emerging contaminants. It's an emerging concern because we're using more pharmaceuticals than we ever have before. And if you're eating it and excreting it into the toilet, that's one thing, but sometimes when medicine is expired, people will just flush it down the toilet to avoid the medicine getting, maybe a child accidentally getting into it, and then that actually adds a lot more of the pharmaceutical to the treatment plant. It's really hard to remove these trace organics because the concentrations are so low. The concentration is really low, and even if there is something, a bacterial species that could live on it as a substrate, there's just simply not enough of it present. And so usually the way that they would be removed is just through this co-metabolic degradation. And that's where it's not necessarily depending on it as a food or as an oxidizing agent, but it's just consuming it incidentally as it's eating something else. It's like, they estimate that the average human eats maybe an ounce of bugs each year, just accidentally, because maybe there was a bug in the food processing plant. And so that's an example of co-metabolic degradation, is you're eating bugs, but you didn't intend to. Maybe it just got into the hot dog, right? So it's the same thing with the removal of trace organics. So the book gives an example of how you could estimate the rate of estrogen uptake, and what it would depend on is partly on how many estrogen degraders are in a wastewater. So if you have the overall biomass concentration, and this N sub E is the fraction of the biomass that can degrade estrogen, but then it's also depending on the mass of estrogen that's present and the first order reaction rate coefficient. So this would be for something that actually can consume estrogen, but ordinarily the concentrations aren't high enough that there is some specific bacteria that's breaking down a certain trace organic. What we hope for is we want trace organics to be biodegradable. And so highly biodegradable, that's a good thing. Because hopefully what that means is that it's going to go out of solution as quickly as possible. So here are some typical concentrations, and what's really amazing to see is how high some of these concentrations are. Like acetaminophen, Tylenol, pain reliever, will have concentrations as high as 67,000 nanograms per liter. So there's, I guess we as a society take a lot more acetaminophen than we do naproxen. Naproxen sodium is also an anti-inflammatory pain reliever. But then some of these are not as biodegradable. They stick around in the environment. So those are the ones that are going to be more problematic if they cause a mimicking effect in species downstream. Okay, lastly, heavy metals. You want to have biological removal of heavy metal. Here is a PPG chemical plant. It's in New Martinsburg, West Virginia. And it happens to be one of the largest contributors of mercury. They discharge really a lot of mercury into the Ohio River. And a few years ago, they got into a regulatory dispute with West Virginia. I don't remember what the name of the agency is. I think Water Quality Board. Basically, the Water Quality Board was telling them they had to measure their mercury discharge by a certain method and try and control it. And PPG said, no, we don't want to measure our mercury discharge, and we really don't want to decrease the concentration that we are emitting. They make chlorine at that plant and discharge a ton of mercury. So mercury causes all sorts of problems. Mercury, when it's consumed by humans, it can cause tremors, gingivitis, psychological changes, poisoning in concentrations that are high enough. Here's just a list of some of the heavy metals, and some of them are bad for people, some of them aren't. So you can see, even though sodium causes high blood pressure, it's not toxic on an acute basis. Iron, you know, some of these heavy metals are actually nutrients that we have to have. But then some of them are actually quite toxic if the concentrations are high enough. Even though you do need to have a little bit of zinc in your diet, if the concentration of zinc in your bloodstream is too high, then it could cause a corrosive effect on the skin, damage to nervous membrane, and so on. So heavy metals are really hard to remove from wastewater. The way that they can be removed is by adsorption. It's not going to be the case that heavy metals provide any energy benefit. There's no energy to be had in heavy metals, and so the way that they are taking them up is that sometimes these charges the metals will have a positive charge depending on if it's an elemental or if it's complexed with an anion. And so if the metal is dissolved and has a positive charge, microbial surfaces often have a negative charge on the outside surface, and so the metal will either be absorbed by the bacteria or just sort of attracted to the bacterial surface and then can precipitate out or can be concentrated through the clarifier. The removal efficiencies vary a lot depending on the concentration of biomass in the reactor and the solids retention time and so on. And so that was just the last constituent that is in most treatment plants, just like how there's very few treatment plants that have a big phosphorus problem that requires tertiary treatment. There's going to be very few treatment plants where heavy metals is a really significant issue. But the ones who do have it as an issue, that may be the thing that they spend more time than anything else dealing with, is just this one special problem or issue that they've got. Okay, so that's it for tonight on the lecture. I know that not all of us got through the in-class exercise, so we'll use the remaining part of that to go through this. Other than that, travel home safe. I hope you are able to get plenty of food and firewood and everything before the snow hits.